Hello and welcome to my second lab. We're going to be revisiting charge tapes. So the key concepts are pretty much the same. Gravitation, your Earth's surface, and Newton's second law. We just need to know this to remember that the net force is going to be zero, and that's evident because the momentum of the tapes doesn't change. They don't really move. They don't change location, actually. As well as that, the electric force, Coulomb's law, which you can see for individual point charges, and then the electric field vector for individual point charges. This is going to be important in evaluating the individual electric fields from parts of the tapes. We're not going to be taking the tapes as one point. We're going to be taking them as a sum of points in a line. So the purpose is to model that. A second computational model will attempt to simulate both tapes' motion, which is going to be zero. And we expect their motion to change according to the equivalent force of gravity and electric force, which are equal and opposite to one another. And this will help us to determine the excess charge. So the key assumptions are pretty much the same. We're going to restrict motion to the y-axis for the tapes. That way, they don't really shimmy in the z or x-axis and increase the distance between them. They only are going to be suspending each other. The net force is also not equal to zero, but only in the sense of the programming for the glow script. And this is going to help us to estimate that charge on the tapes. So the procedure is about the same. You're going to rip off a piece of tape, you're going to put it near the other one, and you're going to see how they interact with each other and how they hold each other up in equilibrium. Remembering that the specific free body diagram for the top tape is going to be that net electric force from the other tape in the surroundings, as well as the force of gravity. Some of the observations that we had from the first part are that they are 1.5 centimeters apart. We also have these other observations that are just basically telling us the dimensions of the tape. If you wanted a super realistic computational model, you would use these. But what we're just going to do is we're going to treat it as a line. And we're going to give it an arbitrary number of points, n equals 10. But it's still important to recognize that they repel one another because they have the same charge. So for part two, though, what we're going to notice is that this is the same force of gravity on the tapes, that the net forces are going to be equal to each other, but that this new force electric is a very different equation. It's given by this equation here, much more complicated than what was on the concept slide. And that's because at the observation location, the center of mass at the top tape, you need to take into account the electric force by each individual point differentiable on this bottom tape here. And so if you sum all of the bottom tapes, which all have this equation, you get a new way to calculate this Q value. And this Q is 6.4 e to the negative 4 coulombs, which is different from the last one. And that's basically because each of these individual points is contributing to pushing away the top tape, pushing away each other, really. And that's super important to understand, is that the tape has a charge which is spread out along its length. So the computational model for this, we're going to remember K and G once more, but we're going to have this new R vector. Instead of just a simple distance, it's going to be a two-dimensional vector with a magnitude R. The gravity is going to be the same. The force electric is going to be made opposite to it, but this new Q is going to have a completely different calculation. And you can see here that this function E field for each individual particle and observation location along the lines gives us this new electric field, and we can sum them to calculate that Q. So for representing the individual parts, we're going to make an arbitrary number of them, n, which I've chosen to be 10, and they're going to each have a part of the charge or a part of the mass, and then they're going to have a part of the field. This dq here is super important in representing that. And this represents all of the individual parts. So the magnitude of total electric force, of total gravitational force, as well as the electric fields from each of the individual parts. You can see them here, top tape in red, bottom tape in blue, gravity yellow, electric in white, and these fields in green. You can see that they're equal to each other, but not exactly. That's because we didn't set them equal to each other. We just fiddled with the code until they pretty much ended up that way. So let's discuss this. The magnitude of the electric and gravitational forces calculated is this new number, 1.926 e to the negative 3 newtons, and that's given by pretty much the gravity calculation. With the less realistic model and observations, the equilibrium between the electric and gravitational force allows us to approximate the charge. This new charge is 6.412 e to the negative 6 coulombs. Actually, it's negative 4. I'm sorry. Regardless, the measurements, the U-tapes not necessarily being perfectly aligned, the broad estimates, and the standard rounding, it's all going to be pretty much the same errors. Moving on, why are these two values different? You can see it's that negative 4, which I had on other slides. Why is it different? If you modeled it as a point charge, the distance is going to be smaller in general. It only has to worry about one axis, not a magnitude of two axes in a sort of triangle. So by spreading out the charge, the distance contributes much more to the force, and therefore you need a greater charge to push the tape away, so to speak. So which value is going to be closer to the real? Well, really, this spread out charges, if you want to say it that way, they take distance much more into consideration with these two axes rather than just one. So the actual value should be closer to the more complex model, which more realistically models the spread out charges. And so a perfect model would actually even include a z-axis with 2D pieces of tape, and that would yield an even more accurate charge.